All right, so now we have a triangle. This is from the iBook, if you want to ever play around with it yourself. The incenter of a triangle exploration, right? If you draw the angle bisector for each three angles of a triangle, the three lines will all meet at one point. And if you look over to the left on GeoGebra, look at this triangle. Look at each angle, like angle A is being bisected. It's 52 degrees, but it's 26 degrees on each side. Similarly with B and C, they're all angle bisectors. Isn't that crazy? They all meet at a single point. I truly find this interesting. I think it's pretty cool. And we call this the incenter. All right, and again, like look, even if I make it obtuse, maybe if I make it right, or close to a right triangle at least, it's always gonna intersect. All right. So things to notice, these black lines are angle bisectors. All right, angle bisector. All right, and then they all intersect at a single point, and again, that's called a point of concurrency. And concurrency isn't a huge word, it's just something like, oh, when all three things intersect, concurrency. But the specific names are what's important, such as this specific point is called an incenter, and it's actually a very well named point. We had the circumcenter last time, now we have the incenter. And now we're going to pull the vertices around and create new triangles. Can the incenter lie outside of the triangle? So how can I get the incenter to lie outside of it? Well, what if I make it incredibly obtuse? Well, no, it's still inside. Well, it doesn't matter what I do, the incenter is always inside. So can the incenter lie outside the triangle? Nah, bro. Can the incenter lie on the side of a triangle? Heck no. That's preposterous. The incenter, I think we'll write that down later. But anywho, all right, we got this nice triangle right here. What happened? That's not good. I have no clue what happened. This went a little, I gotta refresh this page now. Oh boy. There we go. Whew. Crisis averted. All right, now we're gonna drop down these perpendicular segments from I to the sides. All right, so all these green segments right here, they're actually congruent. All right, because remember, an angle bisector, any point on the angle bisector is equidistant to the sides. All right. And then we're going to make a circle centered at point I. So I made a circle centered at point I, and OMG, look, oop, kind of messed up. Time out. All right, it's pretty close, but when you make a centered, circled at the end center, oops. It touches all the sides, so all the points lie on the circle, and this is called the end circle, or an inscribed circle. All right, so now we can get rid of that. All right, so that was just playing around with the angle bisectors. We saw that they all intersected at a single point called the incenter. They're equidistant from the side. So let's just summarize. So the point of concurrency of the three angle bisectors of a triangle is called the incenter. And the incenter of the triangle is always located inside the triangle. So a circumcenter could be anywhere. An incenter has to be inside. The incenter is equal in shortest distance to each side of the triangle. All right. The incenter is the center of the circle. The incenter is the center of a circle that is inside, or you could say inscribed in the triangle. And fun fact, this is the largest circle you can draw inside a triangle. So if you need to draw a circle inside of a triangle, the inscribed circle, the end circle, is the largest one you could draw. I mean, you could draw a circle anywhere, but if you want to maximize the space, you need to draw the end circle. And then 5 and 6 are really good questions. How is the incenter similar to the circumcenter of a triangle? So let's actually take some time and be a little bit thorough on this, all right? Let me think about how I want to do this. So for 5, they're similar because they're formed by the intersection of 3 lines. Let's see, what else? Maybe we'll come back to that, but let's talk about the differences, because I like the differences to be a little bit more thorough. How are they different? Well, let's review circumcenter really fast. That's made by perpendicular bisectors of 3 sides. So your perpendicular bisectors of the 3 sides can lie inside. That's when it's acute. Hypotenuse. That's when it's right. And then outside. That's when it's obtuse. And a circumcenter is equidistant to the vertices. So you could also think of its equidistance to the angles, if you want to reword that a little bit. Or you could say 3 points, because the vertices of a triangle are just 3 unique points. So that's a circumcenter. That's kind of the punchline of the circumcenter. And it might be a good idea to look at some notes from yesterday. And then the incenter is angle bisectors. Only inside. All right, can only be inside, and it's equidistant to sides. So if you need to be equidistant, the point equidistance to 3 sides of a triangle is the incenter. The point equidistance to the 3 angles of the triangle is the circumcenter. So this is useful stuff, like if you need to be equidistance from 3 roads in real life, so like streets, roads, highways, if you need to be equidistance from 3 of them, you need the incenter. If you want to build a shopping mall, equidistance from 3 different highways, that's what you would use. If you want to be equidistance from 3 specific places, such as cities, you'd use the circumcenter. All right. So just some quick follow-up problems, and then we'll call it some notes. We'll call the notes and end. If EG is 23, what is the length of GF? So it's saying, since this is 23, well, what's this length? Well, remember, these are all angle bisectors. It's labeled that angle bisector, angle bisector, angle bisector. All right, so that means that this point G is the incenter. So that means that the incenter is equidistant from the 3 sides. So since EG is 23, GF is also 23. So if you're presented with this problem in the future, if you can identify that's the end center, then you know that point is equidistant from all sides, so it's easily 23. And then since these are angle bisectors, let's look at number 2. This is a good angle problem. It's telling me EAG is 20. So it's saying that this right here is 20. It's telling me that DCG, excuse me, is 30. So this angle right here is 30. Now it's telling me to find FBE. This is the angle I need. Well, remember, triangles add up to 180. So these are angle bisectors, so that means that this side's 20 and that this side's 30. So that means that this whole top angle is going to be 40. So angle A is 40. That means that all of angle C is going to be 60. So that means that using the triangle sum theorem, the measure of angle FBE is plus 40 plus 60 equals 180. A bunch of math occurs, and we get FBE equals 80 degrees.